Hello everyone, welcome back. This is the third lesson on tension in cables, strength of materials and structures. And today we are going to look at the practical application for the cables we have been looking at all along. This is a suspension bridge. You can see that it represents the diagram that we have been looking at all along. These are the two towers or two supports, and we have the cable that is running from one tower to another tower, which will be our cable. We call it the main cable in a suspension bridge, as the one that is on your screen right now. They are the main support. They carry the main load of the bridge. And now, remember when we were defining the catenary, we said the cable must be collapsing on its own weight. On this bridge, the cable is carrying the load of the bridge, connected by these vertical cables that you see. Therefore, we no longer call it catenary because it's not only collapsing on its own weight, but it is carrying the load of the bridge. We now call it a parabolic catenary. We are still going to draw the structure the way we were drawing it, only we are going to include the bridge. And a parabolic catenary is formed when the cable carries a horizontal uniformly distributed load, which will be the bridge. We are still going to draw our diagram the way we were drawing it. The only thing that has changed now is that this cable, which is the main cable, it's no longer collapsed on its own weight. It is also carrying the load of the beam. Therefore, everything will be the same, but the formulas that we use are going to change to accommodate the bridge that we have now. And this is how we are going to do it. We have support number A and support number B. And we have these are the vertical cables that are connecting the bridge to our main cable. We still have a seg of D, and for the bridge to be stable, all the forces acting at any point on the cable, they must be in equilibrium. Still, we are going to have to draw the triangle of forces on each point that we are considering, and we are going to have Ft still. Wx now is no longer Wl as we had on the simple catenary part. Now x will be the distance from the one support to the turning point, meaning this will be xb, and this will be xa, and from support to support that will be L. Therefore we can tell that L is equals to xa plus xb, and then here we have FH. FH is given by W times x squared all divided by 2D. And then Ft will be given by the square root of Wx squared plus FH squared. You can see it's basically the same thing that we were doing on the simple catenary. And if you are dealing with a bridge that has equal support or equal towers, we are going to have x as being equals to L divided by 2. This is obviously the the capital letter W, and the length of the cable is given by the distance between the towers plus 8 d squared divided by 3L, and then everything else applies. We know the maximum tension will be found at the top of the towers. Since they are equal in height, we can just use one side to calculate everything. But as we have already seen from the previous lesson, that whenever we have different height on the towers, then you have to really consider them both and do calculations for each one. But if they are equal like this, you can just consider one side because they are going to be identical. And the minimum tension is going to be at the turning point. Ft minimum is equals to Fh. The minimum tension on the cable is going to be Fh. And there's this formula that I want to bring to your attention in case you come across it somewhere. Let me move this. From this formula, remember we said if we're dealing with a bridge that has equal support, we are going to have our XS being equals to L divided by 2. So we can come here and say our W times L divided by 2 squared 2 times D, and then it will give us this when we simplify. W times, it will be 2 times 2, which will be 4, and then times 2, which will be 8. So it will be L squared divided by 8D. And you might come across this equation. I do not prefer these equations. You do not have to go through all these things. As long as you know that Fh is equals to this, what you can do if you are given L, just take L divided by 2, and then you have your X. Come to this equation, use X, because you might get confused whenever you have to use the different formulas, because here we have 2, here we have 8. You might find yourself putting 8 here and then using X. So I do not prefer this formula. I do not prefer that you come to this stage. Just use W times X squared divided by 2D. That is going to work for you. Here you only put X. Take the L if you are given, divide by 2, and then put it here. Do not go through all these things if you are not sure. But if you trust yourself, then you can come to this. But it is not necessary to even come to this stage. You can just use your X. And you all know we have to understand how questions are asked. How do we apply all these formulas that we see on our screen? Therefore, we are going to do an example from my textbook, which reads as follows. A suspension bridge with supports on the same level carries a uniformly distributed load of 200 Newton per meter. The distance between the support is 80 meters and the sag of the cable is 3 meters. Calculate, those are the questions. Question number 1, the minimum tension in the cable, they're looking for Fh. The maximum tension in the cable, Ft, on the top of the support. The length of the cable, that's number 3. And then number 4, they say the tension in the cable 20 meters from the support. Number 5, the slope in the cable at this point. This is the information that we are given. They are telling us that we are having 2 supports on the same level and they carry a uniformly distributed load of 200 newtons. Now, I want us to go back to the picture that I showed you when we started the lesson. We have 2 cables here. We have this one cable and then we have the other cable on the other side. Okay, let's go back to our question. This uniformly distributed load that they are giving us, because we have two cables and the calculations that we are doing here are based on one cable, the uniformly distributed that they give us, we will have to divide it by 2 because both cables will take half of this load, and this will give us 100 Newton per meter. I'm going to repeat, because we are having two cables, each cable is going to take half of the load that is given to us, and because we are doing calculations based on one cable, we are only going to use 100 Newton per meter, which is half of the load that is given to us, and this 100 Newton per meter is what will be taken by the one cable that we are dealing with. They then gave us the distance between the two supports, which is 80 meters, and then we are told that the sag is 3 meters. We do the calculations now. Number 1, they ask us for the minimum tension on the cable. FH is equals to W x squared divided by 2D. Our W, we are going to use 100 times our X, this is L, 80 is L, therefore our X is equals to L divided by 2. L divided by 2, which is 80 divided by 2, and that will give us 40 meters. Therefore we come here and say 40 squared, all divided by 2 times 3, which is our sag. And here we are going to have our answer as 26.667 kilonewtons. We go to number 2. They say calculate the maximum tension on the cable. Ft, it's equals to Fh squared plus Wx squared. Our Fh will be, we already calculated, 26.667 times 10 to the power 3 squared plus our W is 100 times X, which is 40 squared, and this is going to give us a value of 26.965 kilonewtons. The third question, they say calculate the length of the cable. Let's move this. Number 3, we said the length of the cable is given by L. That will be the total length that we are calculating for here. It's given by L plus 8D squared divided by 3L. And our L here is going to be 80 plus 8 D squared, our D, which is the sag, is 3 squared divided by 3 times 80, which is going to give us 80.3 meters. Let me write these values here because I have to erase. FH is equals to 26.667 kilonewtons, and FT, write it here, it's fine. FT is equals to 26.965 kilonewtons. We then go to question number 4. They say the tension in the cable 20 meters from the support. Remember, we're dealing with only one side, and from here to the support, the distance, which is x, is what? Is 40 meters. Now they are telling us that we have to calculate for the tension 20 meters from the support. It will be in the middle. Therefore, it is going to be 20 meters from the turning point as well, because it's going to be 20 this side and 20 this side. Meaning our x, which will be from here, this is the turning point, to here. Let's say this is point P. Our x is going to be 20 meters. So for this fourth question, our x is given by 20 meters. We can therefore erase this diagram. They said we must calculate for the tension on that point. Our Ft is equals to Fh plus W x squared this side as well. So we know this is always the same throughout the cable. The only difference here that we are going to have, or the only thing that we are going to change, is this x, and then we are going to end up with our Fh is 26.667 times 10 to the power 3 squared, plus our W also doesn't change, it's 100 times 20 squared, and this will give us 26.742 kilonewtons. They then say on the last question, calculate the slope in the cable at this point. At this point, which is point number P. Let's say it's here, P. They want the slope at this point. Let's draw the triangle at that point. FH, it doesn't change, it's always FH. The only thing that we are going to change is the WX, where our X is going to be 20, and as a result our FT is going to change. But we already calculated for FT and we have this, so we can use cos to calculate for the angle. Question number 5, cos theta, this will be our theta. It's equals to FH, which is adjacent, over hypotenuse, and our theta is equals to cos inverse. Our FH is 26.667 divided by our FT, which is 26.965, and this will give us an angle of 4.292 degrees. You can also use tan to calculate for the angle, where we are going to use the opposite over adjacent. But the answer should also be the same as this one. So it doesn't matter which one you use, because in this case we have everything. We can use tan, we can use sine, we can use cos, as long as we are calculating for the correct angle. That is the main thing, because you might find yourself calculating for this angle now, of which is not the correct angle that they are looking for. So you can use any. You can use sine, you can use cos, you can use tan, as long as you are calculating for the correct angle and you have the information that you need for that particular trig ratio that you are using. Notice that for FT, we did not say this was the formula. It's because that formula belongs to the simple catenary. You can also recall from the previous lesson that we did, lesson number 2, when we were told that the note that they gave us at the end of the statement, where they said note no marks will be given for using suspension bridge formulas, they were talking about the formulas that we got today on this lesson, and this one belongs to the previous lesson. If you are doing suspension bridge and they tell you that no marks will be awarded for using simple catenary formulas, these are the formulas they are talking about, the likes of these formulas. You use this formula, you get the right answer. According to you, it's correct, but according to the instruction that they gave you on the question, you were told not to use this formula. Therefore, you are not going to be awarded any marks. Your answer, although it's the correct value, it's not going to be marked correct because you failed to follow the instructions. So this formula, not on this section. It belongs to the simple catenary. This brings us to the end of our question, which brings us to the end of our lesson. I will see you on the next lesson.